Now we're going to continue with amplitude amplification, which is another illustrative way, I think, to see how Grover works. So it's actually the general idea behind Grover's algorithm. So to see that, we will have a look at each of the 3 steps that I defined before. Let us have a look at each of the amplitudes. So remember, we have the first step where we prepare the equal superposition. And then the second step where we apply our oracle, UF. And then the third step where we apply V. So the first step where we create the equal superposition state. Now, if we draw the amplitudes, so let's say we have the state 0, and then 1, and so on. We have somewhere our element W, and then the element, or the other elements until n-1. And here we're plotting the amplitude for each of them. So now in the beginning, if we create the superposition state, we have an equal superposition, so they're all in the state, they all have the same amplitude. And the amplitude, it's not the probability to measure them, but just the prefactor in front of the state is actually the square root of the probability. So it will be 1 over square root of n, which is 2 to the small n for each of them. Each element has the same probability and the same amplitude. And we have no different phases. The phase is always 0 between them. That's why the amplitude is, you can just write the amplitude like that. And so the average amplitude is also just 1 over square root of n. Okay, then we have the second step. The second step is where we apply our oracle, which is identity minus 2 times the projection onto W applied to our superposition state. Let's draw another diagram. Again with the amplitude here. And we have the states 0, 1, and so on. We have the state W, and then the other states. So now what does this operation do? What we know is that on any state except for the state W, it does not do anything. It just acts as identity. So we still have the same amplitude as before. While on the state W, for that state, it flips the amplitude. Because we have now, when we defined the functions, we saw that it projects W for it. When we apply the unitary UF to our state W, we will get the state minus W. So instead of plus, we are here in the minus. The absolute value is the same, but so we're here now. So here we have 1 over square root of n. And here we have minus 1 over square root of n. Which means that the average of all amplitudes is now a bit lower than before, because it's 1 minus 2 over n. That's 1 over square root. Not so important that you follow this math, but I think it's clear that the average now drops because if we flip one of the states. So then we have the third step. And what we do in the third step, we apply our unitary V. also called the diffuser, which is 2 times projection onto S minus identity onto the state that we had before. Again, we have the states 0, 1, so on. W n minus 1. And now what I claim is that the effect of the unitary V is that it reflects all amplitudes about the average amplitude. I want to show you why this holds. So assume we have an arbitrary state. Now we really don't need to care about what our state is, but just look at an arbitrary state. Psi, so an arbitrary pure state, can be written as the sum over some states I that have the phase, the amplitude alpha I. Then if I apply V on psi, this yields the state 2 times the projection onto S minus identity applied to psi. Now if I want to write the projector onto S, then I get twice this 1 over square root of n normalization factor, so I can write 1 over n. I get the sum over all states J, that the sums from over all 2 to the n different superposition states for the cats, but then also for the brass. But I have to do another sum because in both S are both a sum over all states. I have to take 2 different indices and sum over both of them. And then this okay. Let's move that to the next line. This I apply to my state psi, so to the sum over all I, alpha I, minus, and then identity to applied on psi just gives me psi. So just minus that state. Now, I will rewrite it a bit. What I know is we can get the prefactors alpha I can just get them out and just move them to the front. Or actually, what I do is I can then see if I sum over all, if I get the prefactors out, I have the inner product of K and I, the bra and the cat, or the opposite way. Yes. We have the bra of K times the cat on I, which is the inner product of states that are, in general, all orthogonal, except for when K equals I. Whenever K is unequal to I, then it means we have different basis states, so they're all orthogonal, and this inner product gives me 0. So in the end, I don't need to sum over all I, but the only I that gives me a non-zero term is the one where I equals K. In this case, I will get 1. So the inner product with the sum of all I just disappears, and the inner product with K and I is then 0, is then 1 in this case. So what I'm left with is the sum over all K, alpha K over N, and also I still have the sum over all J. Okay, hope this was clear now. Don't worry if it's too math heavy, then just skip this part and just believe me that it reflects the amplitude. So you can also just skip this part. Believe me, it reflects the amplitude. I just want to, for those who are interested, I want to very quickly show how one can see that it actually reflects the amplitude. For those of you for whom this is too mathematical, just don't worry. Just listen again in 2 minutes. And then for the second term here, I just change the index that I'm summing over to J, so that I can do that, right? I'm just summing over it. And now I put these 2 terms together, and I'm getting, so this part is now the average alpha. It's the average amplitude alpha. minus alpha j, it's j, and taking 2 times the average minus an individual alpha j is corresponds exactly to a reflection of alpha j about the average alpha, which one can see again very quickly. So if alpha j equals, I can write every alpha j as some average alpha plus some delta j. And then if I look at 2 times alpha minus alpha j, that would be exactly alpha minus delta j. So instead of alpha plus j, I'm having alpha minus delta j. So I'm having exactly the reflection about the average alpha. So done with this math part, sorry. So what I just showed is that applying V corresponds to reflecting on the average amplitude. So we said our average amplitude was here. Now if I'm reflecting all the states that are not the winning state W, then I'm going down somewhere here. Well, if I'm reflecting the one that is the state W, I can see that it increases by a lot now because we have to add all that up. So we will actually get somewhere here. I mean, I can calculate these values here and here. I don't think that matters too much. You can see them in the notes. But I think it's clear that by doing this, you will decrease the values of all other elements by a lot, or by a bit at least, and then increase the amplitude of the winning element by a lot. And then what we do in Grover's algorithm is we repeat steps 2 and 3. And so by repeating steps 2 and 3, the amplitude of W will increase even further. Which is why we call that principle amplitude amplification. Because the amplitude of this element that we're looking for gets increased, it gets amplified by a lot. And then of course, we learned that the probability to measure a state is given by the absolute value of its amplitude and then squared. So if we have a high amplitude, that means that we also have a very high probability to measure that state, while all other states will have a lower and lower probability to be measured. Okay, so now I would again have time to answer very quickly maybe one question. Afterwards, I will just quite quickly mention how we treat the case when we have more than one marked element, and then I will show you the implementation with Qiskit.
Actually, instead of answering a question this time, Elisa, I'm going to throw you a curveball here because I've been watching the chat pretty intently, and what I see is kind of this back and forth between some people that are saying this is really difficult, a lot of math, and other people saying, you know what, it is, but it needs to be. And I saw one person say, and I'm sorry, I forgot what your username was, but they said, you know, this is a work of art, and works of art are meant to be understood over time. And I thought that was a really great way to say it. So, Elisa, I just want to give you maybe a second or two here or, you know, as much time as you want, to just encourage those people that are finding this difficult to follow, you know, give them some type of encouraging just note to help them stay focused and keep trying.
Yes, so I'm really happy to see so many people attending and trying to follow, even though not all of you have a strong mathematics or physics background. And I mean, the stuff that I'm teaching now is what you would learn, or the stuff that we're teaching during the whole summer school is something that you would learn maybe over the course of a whole semester at university. So it really covers a lot of content. But yeah, we thought that it's better to cover more content, and then people can rewatch the videos and look at the details at home when they have more time than to slow it down too much. So it's on purpose a lot of content, I know that, and I'm really sorry for those of you who are struggling with following me now. But I really would just encourage you to look at it again when you have more time, ask questions, discuss it with your colleagues, it is a lot of content, so really don't feel bad if you cannot follow everything. And I do also assume that people have some math, a bit of math background at least. So if you don't have that, then of course it's going to be much harder for you as well. And yeah,
And I
it
think
is a lot.
A reminder as well. We're proud of all of you for even being here. I mean, many of you have families, have jobs, you're working full time, have many other responsibilities that you're going out and dealing with on top of being in this course. We understand that, and it really is inspiring to have so many people tune in every day and just try their best at this.
Yes.
And so
Thank you, Brian.
that's a great way. Yeah, thank you, Elisa. I think that's a great way to lead into the tail end of the lecture.
Okay, so yeah, now it's the last bit of theory. It's not going to take long. I'm just going to give you a very quick generalization of Grover's algorithm for the case where we have more than one marked element. So far we were saying we have one element that is the winning element. But for example, just when we're looking at some problems that we want to solve that have different constraints, there might be more than one solution in the end. So when we have m marked elements, and with marked elements, I mean the winning elements, the ones that satisfy our constraints, which I now call wi. Then what we do is we define the winning state as a superposition of all these marked elements. So we have to normalize it now. So this is just an equal superposition of all of them. And that also means that our orthogonal element, the W orthogonal, now has a slightly different normalization factor because we have m elements that are not included in it. So it has 1 over square root of n minus m instead of n minus 1, what we had before. But apart from that, it doesn't change. And well, of course, if we now sum over all x, we sum over all x except for all w, all those that are part of, that are in one of the, that are one of the winning elements. So just all others, all that are not in there. So if we then write down S as a sum of W and W orthogonal as we did it before, all that changes is again the normalization factors. We have instead of n minus 1, we have n minus m here. And instead of 1 over n, we have m over n, second term. But again, we just define it by cosine of theta over 2 plus sine of theta over 2. And then the whole algorithm works exactly the same way as described before. We will also rotate by theta every time. However, now the angle theta changed because now sine theta is square root of m over n, while before it was square root of 1 over n. So what that means is that our angle theta becomes larger. So as we rotate every single time by an angle theta, that means that if we have the same number of elements n, but now we have m marked elements, we will actually be faster. So we will, and we can see that also when we determine r. Now the number of rounds that we have to do is this ugly formula, pi over 4 times arc sine of, and now we have square root of not 1 over n, but m over n minus 1/2, which scales as square root of n over m, which tells us the same. If m is, the larger m is, so if, for example, assume every second element would be marked, then this would be a super small number. But okay, even, maybe it's every second element is not what we're looking for, but just if we increase m, our algorithm will be even faster than before, which we can also see when we look at the amplitude amplification. So in the first step, everything stays the same. All amplitudes are 1 over square root of n. We have state 0, state 1, then we have state omega 1, we have state omega 2. I'm not gonna plot more of them now, but there could of course be even more. And then we have state n minus 1. But so they all have the same amplitude. And if we go to the second step, we will now not only flip this one element, so the normal states, the ones that are not marked, will stay the same. But then the state omega 1 will be flipped, and the state omega 2 will also be flipped. And all marked elements will be flipped. Which means that the average now is even, okay, it's maybe too low, but the average now is even lower than it was before. So if you want, I can give you the formula. It's 1 minus 2m over n times 1 over square root of n. So before it was just 1 minus, well, m was just 1. And we can see that if m is smaller, the average will be lower, which makes sense because we flipped more amplitudes. Which then implies that for the last step, if we now flip them all on an even lower amplitude, then these will become even smaller than before. While the other two, well, we have two that are increasing now, right? So they will not be as high as a single element before, but since we have two of them, we have a higher number of getting one of the marked elements now. So, well, what you can just see is that it goes faster because we have the average decreases by much more every single time. But yeah, that's just another way to see it. Now I'm gonna show you how to do that with Qiskit, also for multiple marked elements. I wanted to quickly have mentioned that. Share screen. Can you see my screen already, Brian?
Yep, I'm sorry. Let me focus that for you.
Okay.
And there you go. Now we should see that. Just zoom in a little bit and we should be good to go.
Sorry, what did you say?
Sorry, just zoom in a little bit.
Oh, zoom in. Yes, okay.
Thank you so much.
I guess. Is that fine?
That's good.
Okay, so as for the Deutsche algorithm, again, we start by importing a lot of function, importing NumPy, importing quantum circuit, IBM-Q. It's also like the standard things that we always import, and we load our IBM quantum account. And then now we have to define again our oracles. So this time, I'm not explicitly defining the oracles as I did it for the Deutsche algorithm, because that gets too complicated now. If I increase my n and if I have a specific number of specific marked elements. So what I'm doing instead is, okay, first we start by creating again a quantum circuit where I can give it a name, and the name by default will be oracle, but that's just what you will see later on in the quantum circuit again. And then I'm creating a matrix. So I'm creating a matrix that acts as the oracle. And what the matrix does is applies the minus sign to, it applies a -1 to the, or what it's supposed to do is in the end, it should apply a -1 to the marked elements and just +1 to every other element. So in all other elements, it should act as identity. So what we want in the end is we want a diagonal matrix that has 1s on all diagonal elements that are not the marked ones, and on all marked ones, we want to have a -1. So we create the matrix, oracle matrix, which is just a 2 to the n dimensional identity matrix. And then we go through all indices to mark. So I have here this indices to mark. There's something that I feed the oracle with. I will tell it which indices to mark. And for these indices that it has to mark, it will change the element to the element -1. So we put a -1 on those, while the others stay +1. So this is then a unitary that I have, but now it's a matrix. So what I need to do is I need to transform this unitary, the matrix, into an operator on n qubits, which I'm doing here. And then I apply that unitary. So this unitary I have now applied to the quantum circuit that I created, and I will return this quantum circuit. This is just the phase oracle that I'm creating. Then the other thing that I want to create is the diffuser, which you will see in the Qiskit textbook. They call the diffuser, which I called V. So we create another quantum circuit. We call it diffuser or V. And now the diffuser, what it does, let's maybe look at the circuit here on the side. The V matrix consists of first applying Hadamard gates. So we apply Hadamard gates to all n qubits. Then we apply the phase oracle. But the phase oracle now, it's basically the oracle which takes as marked element just the 0 element. So the element 0 that I'm giving it is the element 0000 on all n qubits, which is exactly the one that is marked in our second oracle. So we apply the oracle on the 0 state, and then we apply another, again, Hadamard gates on all n qubits. And we return that quantum circuit. And now that's all we need. Now we can just construct the Grover algorithm. We start by creating a quantum circuit with n qubits and n classical bits, so that we can, again, in the end, do a measurement, because of course we want to find the elements, so we need to do measurements in the end. So we have our n classical bits as well. Then we determine R, the number of rounds that we want to apply. Now we have this ugly formula here. Here we go. So we have, or actually, let's show the general one for arbitrary m. Here we have pi over 4 times arcsine of square root of m over n. So m is the length of the marked elements, because the marked elements I will give an array which can have any number of elements. I can just give it with 1 element, but I can also put in 5 elements. So, but the length of this array will tell me how many marked elements I have. And 2 to the power small n is what gives us the capital N, the number of possible bit strings. So this is square root of m over n, taking the arcsine 4 times pi over that minus 1/2. And now, of course, I'm probably getting something that is not, like I can get 5.3, but I need to have an integer number, so I'm rounding that number. And I'm also taking integer, because if I'm just rounding it, it's still probably a float or double. And then I take the integer, so I can do a for loop later on that. So just as to see how many rounds I'm actually doing and what my marked elements are, I'm then just printing the information. That's not important. It's just for me to see what I'm actually doing. I'm trying to find these marked elements, and I'm doing it by applying Grover algorithm with R rounds. Then in the end, I am applying, sorry, not in the end. Then I start my quantum algorithm by preparing the state S, the superposition state. So I just created the quantum circuit with n qubits, so they're all in state 0, and I need to apply Hadamard gate to all of them to get the state S. Once I did that, we have R rounds. So this is just a dummy indice, which means I don't need it. I don't need to use whatever index I'm using to go through all the R rounds, just doing R rounds, the same thing. So I have R rounds in which I append first the phase oracle, where you can see it had n as I need to give n, and then I need to give the indices that I want to mark. The indices is just the marked elements, which I also have to feed to my Grover algorithm. It's the elements that I'm looking for. So I apply the phase oracle with n and marked, and I apply it to my n qubits. So I need to specify that as well if I want to append that quantum circuit to my original, to the QC quantum circuit. After I appended the phase oracle, I append also the diffuser. So the one that is H, UF0H, and also on my n qubits. On all of that, I do R times. In the end, I do a measurement on all n qubits and store it in all n classical bits. And then I return this quantum circuit. So now I can run that. And let's choose, for example, n equal to 5. Then x is just, now I want to, my marked element, I just want to choose a random number between 0 and 2 to the n minus 1. So this is how I do that. So I don't need to give it a specific one, but I just choose a random one. And then I run Grover and I draw the circuit. Okay, so now you can see the information that I printed is I have 5 qubits. The basis state that I've marked is the state 2. And this means that I need to run 4 rounds, given 5 qubits and 1 marked element. So we see we have Hadamard on all qubits, then oracle, diffuser 4 times. And then the measurement in the end, and then we will get the outcome. So this is just as expected. Now let's see what happens if we run it on our simulator. So we again choose as backend, just as we did with in the Deutsch-Jose algorithm, we choose the QASM simulator to be our backend before doing it on an actual device. Then we then we run the whole thing by using the execute command. We execute the quantum circuit that we just constructed using our simulator as backend and with 10,000 shots. You will see in a second why I'm using 10,000 shots here, because then I'm getting the results and the counts, and as before, I plot the counts. I plot the counts in a histogram. So let's run that and see what happens. So what we can see here is the probability to get the state 2, which is the one that we wanted, right? We saw here that the random element that was chosen was element 2. And we can see this is the binary description of the number 2. And it's 0.999%. Oh, sorry, 99.9%. The reason why it's not, but that's basically, by the way, the reason why I wanted to have 10,000 shots, because if I would only choose 1,000 shots, it might have just showed you that it's probability 1. And I wanted to show you that it's not probability 1. And this is not because we have any noise, because we're using the simulator, so there is no noise. But the reason that we have not probability 1, but still a very high probability, is that if I compute the R without rounding it, if I just look at the formula that I would get, actually one that I showed you before, I'm getting 3.92. So then this is rounded to 4. But 3.92 is already quite close to 4. So in the worst case, we would get something like 3.5. And then we would be as close as 1 over 2 to the n, which is the error that we calculated before, the failure probability that we would have in the worst case. But in our case, as we have 3.92, it's already very close to 4, but it's not exactly 4. If it's exactly 4, we would get exactly 1 here. But since it's 3.9, we get something still very high. So we can see the success probability is actually pretty high. Well, now we can run the result as well on our backend. But actually, I'm not sure whether I want to do that because I already ran it before. I can run it now. I'm choosing, but we have to decrease the number of qubits so that the noise is not too high. And we can now see here, shot is being validated. But I also ran it actually before to show you the results. And the results that we got here was that. And you can see there's quite some noise, but you can still identify what the 2 marked elements were in this case. In the case where I ran it before, we got the 2 marked elements 1 and 2. So the binary description of 1 and 2. While the others also had some probabilities, but this is, first of all, it's of course because, well, probably we had to round R a bit, but then also because we have noise on the quantum computer, we have to apply a lot of C0 gates, and then, yeah. Okay, so that's actually all I wanted to show you.